All right, we're back. Chapter 11. Chapter 11 is pretty short. On to it. Section 11.2, multinomial. So multinomial means many numbered experiments. So in the past, we were able to test claims about one proportion or perhaps two proportions at a time. So we would have something like this. Test the claim that 14% of Americans do whatever. The important part here is it says test the claim that 14%. So that's a claim about one proportion. And we would write down the claim just like this. We've got one proportion, it equals 0.14. But what if we are supposed to test claims about 3, 4, 5, or 6 different proportions? We don't want to do 5 or 6 different tests. We want to be able to do one test and be done with it. So here's an example. If you think about the students that attend Hartnell College, test the claim 62% are Latino, 24% are Caucasian, and 5% are African American. One quick note, notice that doesn't add up to 100%. It doesn't have to, because we're just saying for those three groups, this is what we think the percentages are. Obviously, there are a lot of other groups that aren't included, so this doesn't add up to 100%. That's okay. We're just testing the 62%, the 24%, and the 5%. So our claim would look something like this. Group number 1, 0.62, group number 2, 0.24, group number 3, 0.05. And like I say, we want to do one test to see if those percentages seem correct or not. All right, the test in this section is actually called the goodness of fit test, because what we're trying to see is if we actually go out and collect data at Hartnell, are the percentages going to seem correct? So the number of people that say they're Latino, is that going to be close to 62%? The number of people that say they're Caucasian, is that close to 24%? How well does the data actually fit those percentages? So with the new test comes a little new notation. The O are the observed values. In other words, when you actually go out and count and ask people which group they believe they belong to, that's how many people would be in each group. And then the E is basically saying, well, this is what we expect. If the 62% is correct, here's how many people we think would say Latino. If the 5% is correct, here's how many people we think would say African American. That's what we expect if those percentages are correct. K would be the number of categories, which in the last example I did was 3 different categories. And then, just like always, N is the sample size. So you may remember binomial situations. We find the mean by putting N times P. So you would take the total number of people interviewed, and then for example, for African American, this would be 0.05 to find out, in theory, what do we expect? How many people do we expect to be in that group? It's also called the expected value. Expected value is just another word for the mean. So the expected values are going to be found by N times P. The test statistic is chi-squared. And this formula right here is not in the calculator. We're going to need to do this ourselves. But what you do is you just subtract the observed values minus the expected, square it, and divide by the expected. Do that for all 3 categories, add up the 3 fractions, and you're done. That's the test statistic. Since we're dealing with chi-squared, then it's going to be table A4 for the critical values. One thing that's slightly different is degrees of freedom is k minus 1. So the number of categories minus 1 is degrees of freedom. One other thing that's slightly different is no matter what the claim looks like, these are always going to be a right-tailed test. So whatever alpha is, that goes in the right tail, which is nice. It narrows it down, just one possibility. Okay, on to our first example. It's going to be about tardies, people showing up late in one of my calculus classes. So I kept track, well, I always keep track of tardies and absences, but I went back and looked, and I tallied up for a few weeks how many tardies there were on Monday, how many tardies on Tuesdays, etc., etc. And this is what I found. These are the observed tardies, or the observed values. The next thing to do is add those up. So if you just add up the 16, 8, 10, etc., you'll get 60 tardies total. And since it's Monday through Friday, that is k equals 5. Next up, you find, so expand the table a little bit, make another row, and you find the expected values. Since it says same, there's actually two ways to find the expected values. One is, if they're all going to be the same, you could take the total of 60, divide it by 5 days a week, and you'll get 12. So all of these should be the same, 12. The other way is, if they're the same proportion, well, 5 days a week would be 100% of the school week. Divide that by 5 is 20%, so each of these should be 20%. Well, it's 20% of 60 tardies, so if you take 20% of 60, you also get the number 12. So this is also coming from n times p, n times p, n times p. You get the same thing, 12 for each day. Next, for the chi-squared. So what you do is just take each pair of numbers, 16 and 12, subtract them, square it, and divide by the expected value. Do that for the 5 fractions. Type that into a calculator to see how much is it when you add up those 5 fractions. It's a grand total of 3.833. So that is our test statistic, 3.833. Okay, the claim would look like this. So I put it as, here's Monday, 20%, Tuesday, 20%, Wednesday, 20%, etc. You don't have to write down HO and H1 and all that, you just write down the claim. Since it's chi-squared can't be negative, so it starts at 0. It's a skewed distribution. And like I said, it's a right tail only, so alpha equals 0.05 goes in the right tail. Degrees of freedom is k minus 1, so that's going to be 4. And next, to look up the critical value, we need table A4. So I've got one around here. Oh, there it is. With this table, we're looking for the right tail only, so we're going to be using this 0.05 on the right side. Degrees of freedom is 4, so that's going to be this right here, 9.488. So the critical value is 9.488. From the previous page, remember that chi-squared, the test statistic, was 3.833. And now the question is, does the 3.833 go past 9.4? No, it does not, which means that we didn't prove anything. More formally, you can say failed to reject the claim, but we basically did not have enough data to make a conclusion, which is basically saying that 60 tardies is not enough data. If you want to prove something, then you really need more data than that. Okay, so that's the first type of example when they say they're all the same. Next, when they're different. Example number 2. So I got this from the Monterey Herald, and they were talking about how people get to work. So they said for Monterey County, 67% drive in their car alone, 17% carpool with at least one other person, and 2% take public transportation. For Monterey County, I believe that means bus, but they said public transportation. So there are 30 people that I asked. It was actually a stat class. There were 42 people total, but only 30 of them worked. So I asked those 30 people that did go to work how they got to work. And here's what it is. Now let's make sure this adds up to 30 people. 22, that's 28, 29, 30. Oh, good. So there's 30 people total, and here's how they got to work. Either alone, or in a carpool, or public transportation, which I'm just abbreviating the bus, ride the bus. So then for each category, I use n times p, so 67% of 30. So in theory, this should have been 20.1 people. In theory, this should have been, there's an equal sign missing right here, equals 0.51. In theory, this should have been a 5.1, and in theory, this should have been a 0.6. Next, for, why does that say 32? Make this a 30, sorry. N equals 30 people. Categories 3. And let me just check these numbers. So you take 22 minus 20.1 and square it, divide by 20.1. 6 minus 5.1 square it, divide by 5.1. 2 minus 0.6 square it, divide by 0.6. Put all that in a calculator and you'll see that the test statistic is 3.605. Next, we need the graph. Oh, my nice little arrows. There you go. Next, we're going to need the graph. So the degrees of freedom is k minus 1, so that's a 2. Again, it's a right tail, and we're going to use 0.05, so it's 5.991. 5.991 is the critical value. There's a nice little picture, degrees of freedom 2, critical value 5.991. And again, does this 3.605 go past the 5.991? Well, again, it does not. So again, failed to reject, we cannot prove anything. Sample size wasn't big enough. So that is section 11.2. I hope you enjoyed it as much as I did.